In computer science, the iterated logarithm of n, written log *n, is the number of times the logarithm function must be iteratively applied before the result is less than or equal to 1. The simplest formal definition is the result of this recursive function. On the positive real numbers, the continuous super-logarithm is essentially equivalent. But on the negative real numbers, log* is 0, whereas for positive x, so the two functions differ for negative arguments. In computer science, lg* is often used to indicate the binary iterated logarithm, which iterates the binary logarithm instead. The iterated logarithm accepts any positive real number and yields an integer. Graphically, it can be understood as the number of zigzags needed in Figure 1 to reach the interval 0, 1 on the x-axis. Mathematically, the iterated logarithm is well defined not only for base 2 and base e, but for any base greater than. Analysis of algorithms. The iterated logarithm is useful in analysis of algorithms and computational complexity, appearing in the time and space complexity bounds of some algorithms such as finding the Delaunay triangulation of a set of points, knowing the Euclidean minimum spanning tree, randomized time, Furor's algorithm for integer multiplication, finding an approximate maximum, lg*n-4 to lg*n plus 2 parallel operations. Richard Cole and Uzi Vishkin's distributed algorithm for 3-coloring an n-cycle, synchronous communication rounds, performing weighted quick union with path compression. The iterated logarithm grows at an extremely slow rate, much slower than the logarithm itself, for all values of n relevant to counting the running times of algorithms implemented in practice. The iterated logarithm with base 2 has a value no more than 5. Higher bases give smaller iterated logarithms. Indeed, the only function commonly used in complexity theory that grows more slowly is the inverse Ackermann function. Other applications. The iterated logarithm is closely related to the generalized logarithm function used in symmetric level index arithmetic. It is also proportional to the additive persistence of a number. The number of times one must replace the number by the sum of its digits before reaching its digital root.